Okay, so I'm going to take a few minutes and go through the general characteristics of bonds. And I'm going to go through them in a particular order. We're going to start with network solids, then ionic, metallic, hydrogen, dipole, nonpolar. The reason why I'm going through them in that order is because that's also the strength of the bonds from strongest to weakest. So what we should know about network solids is that they are covalent and they have the highest melting point out of all of the bonds, and that should make sense because we had said previously that bond strength is directly related to melting point. The stronger the bond, the higher the melting and the boiling point. They are non-conductors. And two examples that you should be familiar with, especially for the reagents, are diamond and sand, which is your silicon dioxide. And that's all you have to know about network solids. Moving on to ionic. Ionic compounds are between a metal and nonmetal. There is a transfer of electrons. And you should know that the transfer is from the metal to the nonmetal. They have high melting points, not as high as the network solids, but still pretty high melting points. And they conduct when liquid or mixed with water. And we refer to that as aqueous. So for example, if I had sodium chloride, NaCl, it wouldn't just conduct in the solid state. We would either have to heat it up high enough so that it would melt in its pure form, which is above 800 degrees Celsius, or we could mix it with water. Once it's mixed with water and it's aqueous, the ions will separate. Remember, in order to be a conductor of electricity, you have to have mobile charge. You either need mobile electrons or mobile ions. An example of an ionic compound, as I said, is NaCl, where Na transfers its one electron to Cl. Remember that when we write Lewis dot diagrams for ionic compounds, we have to have brackets around what's gaining, and we need charges. So chlorine gained 1, Na gave up 1. The one that's gaining is always negative. I'll do one more. How about MgCl2? So in this case, Mg wants to give up 2 electrons. It's going to give 1 to chlorine right there, and it's going to give its second one to another chlorine. So each chlorine gained 1, so they each have a negative charge, and the Mg lost 2, so it's going to have a +2 charge. All right, let's move on to metallic. Metallic is simply metal ions in, they like to use the term, a sea of mobile electrons. So it's simply metal atoms, a bunch of gold atoms or a bunch of silver atoms, ion, surrounded by a bunch of electrons. And it's of the same element, so it's all gold or all silver. They also have high melting points, and they are good conductors. Moving on to hydrogen. Hydrogen is a special type of dipole when hydrogen bonds to NOF. When H bonds to nitrogen, oxygen, or fluorine. So an example of this would be NH3. And it's got 5 valence electrons, and then H comes in, each on one side. Notice that there is no brackets in charge. That's because there is a sharing of electrons. Hydrogen bonds are also polar, meaning that there is pull. So in this case, the pull is in the upward direction. So I have a dipole moment this way. So they are also polar, which means that there is an unequal sharing of electrons. As soon as you have pull in a molecule, you have an unequal sharing of electrons. Dipole means 2 poles. So as with the hydrogen, you have a slightly positive and slightly negative side. The negative is always by the element with the higher electronegativity. Now, to determine where the partial charge is, you always have to draw the molecule. So, as in with HCl, chlorine has a higher electronegativity than the H, so this side slightly negative, this side slightly positive. So my dipole is toward the chlorine. Polar molecules are also known as asymmetrical. And there is also unequal sharing of electrons. And the last one is nonpolar. So when we get to nonpolar, we have to think about things a little bit differently. We can be nonpolar if we are Brinkelhoff, B-R-I-N-C-L-H-O-F. So that means, for example, I'll use N2 as an example. So I've got N with a triple bond, bonded to itself. So the electronegativity difference is equal to 0. So any of the Brinkelhoffs, their electronegativity difference is going to be equal to 0. They are going to be linear, or what we call symmetrical. Therefore, there is an even charge distribution. This is the weakest of all bonds, and they have low melting and boiling points. Now I can also be nonpolar if I am symmetrical, as in CH4, CCl4, and CO2. So these are the most popular. Let's take a look at what these look like. I've got C, H4, and then if I did CCl4, it's going to be the same thing, but I'm going to have Cl's around it. And don't forget, you've got to draw all of the valence electrons. Each chlorine's got 7 valence electrons. You have to make sure that you draw all of them. Otherwise, your diagram is not correct. And then you have CO2, which I've preached to you about in the past, that you need to know how to draw. So CO2 is linear in shape, okay, and it's symmetrical, so it's nonpolar. And both CH4 and CCl4 are both tetrahedral in shape and nonpolar because they are symmetrical. So there is an even distribution of charge. One thing that we have to know about all of these, so these last 3, is that they are all poor conductors, and they all have low melting points. And they're usually a solid, or a soft solid, a liquid, or a gas. Now, when we talk about specific forces, intermolecular forces, we've got the hydrogen bond, which is here, when hydrogen bonds with NOF. So this is a type of intermolecular force. Then we have dipole-dipole. So this is our dipole-dipole here. And then we also have London dispersion forces. And London dispersion forces, these are our LDFs right here, our non-polar molecules. Now, if I want to take this one further and give you an example of this, I could. Now, I don't expect you to know how to draw this, but let's say I had 2 water molecules. So the forces that we're talking about when we talk about hydrogen bonds, we're talking about a force between 2 water molecules. So when the H of one molecule is attracted to the O of another, that's what we're talking about when we talk about the intermolecular forces, the hydrogen bonds. And I could have another one over here. Those are my hydrogen bonds, those intermolecular forces between the molecules. Now let's look at a dipole-dipole and see how it compares. So here's 3 polar molecules, 3 HCl molecules. So my dipole exists between the molecules. So there's my dipole-dipole. So when we talk about intermolecular forces, that's what we're talking about. And London dispersion forces would be very similar. And that pretty much sums up the bonding general characteristics. Again, this is pretty much what's on your sheet, but I've explained it a little bit more, and hopefully that makes sense. Remember, never imagine me having dirty napkins. Helps you remember the strength. Network solids are the strongest, followed by ionic, metallic, hydrogen, dipole, and nonpolar last.